Alright guys, so we are continuing vector talk, and it's time to start getting into some modeling. Alright, application. When are vectors used in real life circumstances? And so, we've talked a lot about vectors so far, but basically just kind of algebraically, hardly calculus based really at all so far. One of our main reasons for kind of showing vectors, especially towards the end of our Calc Honors class, that we are dealing with, is to start thinking about vectors in terms of the motion of objects moving in a coordinate plane itself. All right, and so we're going to start looking at some vector problems, and you may have already seen some vector problems in a physics or a mechanics course, or maybe in engineering or something of the nature. And so hopefully this is going to be kind of a somewhat of a review for us. And so let's take a look. The example we have is a Boeing 727 airplane flying due east 500 miles an hour in still air. It encounters a 70-mile tailwind acting in the direction 60 degrees north of east. The airplane holds its compass heading due east because of the wind, acquires a new ground speed and direction. What are they? All right. So first and foremost, I think we should start kind of thinking for just understanding what is the relationship between each of these different components that we are dealing with. All right, I guess I shouldn't say component because we are dealing with vectors, but I guess it could be components as well. I want to first and foremost kind of just draw the representation. Let's kind of think about what's happening here first and foremost. So here's our axes that we are dealing with. And it says that we are flying due east. And so due east, we're flying due east. And so that means I'm going to follow exactly east on here. And it says 500 miles an hour. And so the length of our vector, the magnitude of our vector, is going to be at 500 miles an hour. And then it says it encounters a 70-mile an hour tailwind that is 60 degrees north of east. 60 degrees north of east. And so my vector here, all right, is 70 miles an hour, and it was created 60 degrees north of east. So this value is 30 here, right? So it's 60 degrees north of east. All right, well, what are we really trying to actually find? It says that because of this tailwind, all right, it acquires a new ground speed and a new direction. All right, well, what's this new ground speed and the new direction? Well, think about what happens. You're going 5 miles an hour east, but then all of a sudden you have to take into account, well, oh, no, there's a 70-mile-an-hour tailwind. Now what happens? Well, now it becomes the sum of these two vectors. It becomes the sum of these two vectors. So u plus v gets created. And take a look there. There is our parallelogram representation, right? So here's kind of our u plus v. All right, so I say let's go ahead and say, hey, let u be, we're going to say let u be the velocity of the airplane. So u will be the velocity of airplane. And let's say that our v is our velocity of our tailwind happening here. Okay, so let's think about this for a sec. The magnitude of the velocity of the airplane alone, we already said, had a size. A magnitude of u is going to be equal to 500. The magnitude of v in this case is going to be 70, because it said our length, or quote unquote, our length was going 500 miles an hour. And so now, what do we actually need to find? We need to find the magnitude and the direction of the resultant vector, or the addition of these two vectors. And so what do we do to kind of represent this? Well, we need to find out what these look like in actual vector and component form. And so u in component form is going to end up equaling 500, right, comma 0, because it went 500 degrees towards x and 0 degrees up towards our y direction. So what about v, though? What about vector v in this case? Well, I want to go ahead and I want to redraw. So let's draw our axes down here. Let's use our purple once again for vector v. And so we have our vector v had a 70 mile per hour length. And so how can we actually go about finding the length of the component form, I should say, of vector v? Well, you got to kind of think of what is given. Well, in finding u was pretty simple. It was 500 units to the east, and they didn't go anywhere up or down. And so now it's like, all right, well, what is the concept of to the right how many units and up however many units? Well, now we're thinking about what we talked about using our thoughts of cosine and sine. Because remember, it is true that in this example here, the cosine of 60, and it's 60 in this case because we said that we are 60 degrees north of east. So cosine of 60 is equal to x over 70, and sine of 60 is equal to y over 70, which gives us the component form as a cross multiply, that the x values will be 70 times the cosine of 60, and y would be 70 times the sine of 60. So this is what our v is. So let's go ahead and identify v as 70 cosine 60 and 70 sine 60. All right, so now we've gone ahead and found out what u and v are. But remember, the goal in the end was to find out what the resultant was. Remember the resultant force, the resultant vector of u plus v all together. That's what we really want to find. So taking a look, u plus v in this example ends up being 500 plus our 70 cosine of 60, which gives us 535, because 70 times cosine of 60 is 35. Let's do these values real quick. 70 times cosine of 60, that's a value of 35, because it's 1/2 times 70. And then for our sine of 60, we end up getting square root of 3 over 2 times 70, so we end up getting 35 root 3. All right? And so 500 plus 35 is 535. And then 0 plus 35 root 3 is our 35 root 3. So that is the component form of the vector. But we're not quite done yet. It says, what is the new ground speed? So what is the miles per hour of u plus v? Well, if 570 were the magnitudes of u and v, I need to find the magnitude of our u plus v, our resultant vector. And so the magnitude of u plus v in this case is the root of 535 squared plus 35 root 3 quantity squared, not cubed. And then this ends up roughly being 538.4. And so there is our new ground speed that we're dealing with. But we're not quite done. It said and direction. So what is the new angle being created here? Well, let's think about this for a sec. If I have my new, I guess, quote-unquote, creation of u plus v, my resultant vector, well, how can I go about finding our new directional angle? Well, if you remember correctly, the angle, all right, is going to be that new focus, I guess, that we have, all right, from u plus v. Well, remember, u and v, u plus v, this is the y, and this is, or excuse me, this is the x, and this is our y. So if I don't really necessarily want to deal with a hypotenuse, quote unquote, right, or r that we think about in trig functions, we can think about our x and our y. Well, x and y, that's just opposite over adjacent. That's all that it is. It's just opposite over adjacent, or tangent. And so we can, I'll go to the very top here, the tangent inverse of y over x. Remember, tangent is y over x. 35 root 3 over 535, and we end up seeing that the tangent inverse gives us a new degree direction of 6.5 degrees. All right, and that is going to wrap up this example, ladies and gentlemen. And we're on to the next one.